Get started?
Yeah, let's go.
All right. Well, thank you all for joining us today for our webinar, A Different Kind of Quantum Circuit, Exploring Atomtronics with Oqtant. My name is Alex Tingle. I am the Technical Product Manager for our quantum matter products, which includes Oqtant. I'm joined here today by Yewei Wu, who is a quantum physicist working on the Oqtant team. Today, we're going to go over a handful of things. We wrote this webinar with kind of an audience in mind who has a foundation in electrical engineering and circuitry. However, I wanted to put down a good foundation so that even if you're less familiar with that side of things, there'll still be some really interesting things to take away. I'll then introduce Oqtant, and then I'll hand it off to Yewei to kind of dive into the meat of why we're here today, to look over Atomtronics, do some look into the different elements and do some classical analogs, and then he'll actually take us through a live demo using Oqtant. And we'll wrap up with kind of some next steps so that you can apply what you learned here today and do some fun projects on your own. You'll probably notice that we're not in your typical conference room. We're actually here in the Oqtant lab. So what we have is the machine is online right now. It's buttoned up, not just so we don't have to wear laser goggles right now, but also we are actually running customer jobs while we're talking. So if you submit a job right now, it's running on the machine behind us. If you look at this, if you look at this little screen, every time that flashes, that's a different job that shows us a picture of the atoms in one of the first steps. So every time it flashes, that's a different job. So a fun little Easter egg for you. So let's start with just an overview of quantum technology. You can split quantum technology into kind of two different historical phases, 1.0 and 2.0. 1.0, this is what we have been living in and revolutionizing the last and current century. So these are devices that are quantum enabled. They use quantum mechanics, and we wouldn't be able to have this webinar at all if it weren't for quantum 1.0. 2.0 is kind of the hot topic of the day. This is what we're calling, the quantum industry now. So these are devices that actively create, manipulate, and read quantum states. They can measure things like superposition and entanglement, and many consider it the marriage of quantum physics and information theory. Just for some examples, this is a lot of what Quantum 1.0 has enabled. They're quantum-enabled devices. At the heart of it are things like semiconductor junctions and transistors. Without these, we wouldn't have cell phones with which to take photos of cats playing with laser pointers, arguably the most important application of laser technology. Lasers themselves are Quantum 1.0. And then I added this just because I really like this animation of an MRI, which a lot of people might not know actually is a quantum-enabled device. It's based off of a physical phenomenon of nuclear magnetic resonance, which is a union of quantum mechanics and classical electrodynamics. 2.0 are fundamentally quantum technologies. I have 2.0 as near, but let's be honest, it is here. Even on the commercial side, you can access quantum computers over the cloud. You can order quantum devices. At Cold Quanta, we are working on many of these devices, including quantum clocks, quantum navigation devices. So these are like inertial sensors or gravitational sensors. But there's a wide variety of things, including bioimaging, secure communications, cryptography, and more, including Oqtant. You can get online with Oqtant right now. So it's not just near, it is here, but it is a growing field. So let's start with cold. You'll hear the term cold atoms thrown around a lot. Our company actually started as Cold Quanta. So why do we care about cold so much? Well, quantum systems, just like classical systems, do a lot better if they are isolated from their surrounding environments. With quantum, that often means getting cold. And doesn't just go for cold atoms. If you look at superconducting and quantum dot quantum computers, they also require cold. And the way they do that is these really beautiful, they look like chandeliers, but this is actually a dilution refrigerator. And this helps get the quantum computer below 4 Kelvin. Now, on our side of the world with atom and ion-based quantum systems, we can go even lower, like orders and orders of magnitude lower, using atoms and ions in vacuum, which is a great way to isolate it from the environment, and using techniques like laser cooling, which also takes advantage of, we take advantage of magnetic fields. This photo right here, we took it in our production facility because we build these for ourselves and others. This white glowing dot, those are atoms, similar to the little screen you see up here. So these are cooled, they are trapped atoms. Why do we care about atoms other than the fact that most of us here are kind of obsessed with them? We have our favorites. Mine's rubidium. You can cool them down a lot cooler than anything else. Actually, what we're doing right here is colder than any place in the natural universe, not just any place on Earth. This is a picture of the Boomerang Nebula. Sorry, Boomerang Nebula, we're a lot colder than you. And we can do all of this without refrigeration in our vacuum. This is also the reason that Yewei and I are not wearing parkas right now. And the reason we believe in cold atoms as like the dominant quantum modality is because they are so flexible, but most importantly, they are truly standard and self-calibrating. You don't have to teach a rubidium atom how to be a rubidium atom. So that makes it a really compelling candidate for applications where calibration is either impractical or just undesirable. So if you consider deep space navigation, deep ocean navigation, or just places where you really don't want to have to worry about GPS getting spoofed on you, atoms are awesome for that. So if we take everything a step further from cold atoms to ultra cold, we can start getting into the realm of quantum matter. Quantum matter is kind of actually a broad subject, but it describes phases of matter whose properties are intrinsically quantum mechanical. So the phases of matter most of us are familiar with are solids, liquids, gases, plasmas. These are all described classically. Quantum matter needs to be described quantumly. But this also means that you can look at quantum mechanical effects at macroscopic scales. Now, what we're doing here is a type of quantum matter called a Bose-Einstein condensate, often called the fifth state of matter. And we do this by, just to give you a sense of scale of how many orders of magnitude colder that system is. BECs are the ones we make regularly that we don't even think about are at around 100 nanokelvin. So you can see how many zeros after the decimal point we are looking at. So really just a hair above absolute zero. The Boomerang Nebula, the coldest place in the known universe, that's about 1 Kelvin. The coldest place on Earth, already getting to a toasty 175 Kelvin. That's actually very, very cold for us on a human scale, because at room temperature, we're sitting at around 293 Kelvin. Just an interesting point of fact, the first Bose-Einstein condensate was experimentally demonstrated just down the road from us, actually at Yewei's and my alma mater, CU Boulder, University of Colorado, and JILA. And it was shortly thereafter demonstrated at MIT, and those researchers were awarded the Nobel Prize for that work. And now you can log in for free, click a couple buttons, and recreate it. I obviously get really excited about this. But other than it just being a really interesting field of study, why do we care about quantum matter? So to understand why we care, let's understand a little bit more about quantum matter. So when atoms occupy the same quantum state, they can be correlated even when they are separated by a large distance. This is known as quantum coherence. We can actually use Oqtant to observe quantum effects like superposition and interference on a macroscopic scale. So a big thing, not just a single atom, by splitting and recombining our BECs using optical barriers and landscapes. And we'll go into a little bit of what that means in a minute. But this is a picture, like literally a picture of a Bose-Einstein condensate. It is cigar shaped. So we created it, and then we used laser light to cut barriers, thank you, Yewei, into the condensate. So even though it looks like three completely distinct things, they are coherent. Things like interference are actually critical for designing quantum sensors that use quantum matter. And then with this, you can also explore frictionless superfluid flow of BECs and engineer quantum currents, which is kind of the hot topic for today while we're talking about Atomtronics. So how did we get here? Cold quanta has been around for 17 years, and we have been not just studying and being world-leading experts in cold atoms, but we have been commercializing it. We have been building and selling these cute little compact vacuum systems for most of that time. And Oqtant gets to benefit from that design heritage. This quantum matter machine located behind us is at the core of the cloud product that you can access from wherever you are. And just really cool, a version of this lived on the International Space Station for about 6 years. I think it just came down, but that launched into space in 2018. So even though you see all this glass and you think it might be pretty fragile, I mean, I beg you not to drop a wrench on it. But it made it to space, where astronauts were actually able to perform cold atom and quantum matter experiments in microgravity. So let's dive into what Oqtant is. So it is a very versatile cold atom lab for research, education, and also technology development. And you can access it over the cloud today. This is a screenshot of our web application. This is also where Yewei lives. So he is in charge of making sure things run smoothly. He's the captain of the ship here. You can access the system in a couple different ways, but no matter how you do that, it looks kind of in the same flow. A single shot experiment is what we call a job. So you design your job, you submit it, it goes into a global queue, it runs on the system, and then the system returns your data to you. You can start with our web application with the user-friendly GUI, but we also have a more powerful Python API, which is what Yewei will take us through with the demo here in a bit. Now let's look behind the curtain. Here's the quantum matter machine. I think this is probably the 20th time I've shown this so far. This cabinet contains a lot of the control hardware, which includes our computer, our lasers, and different control cards, say to like control our magnetic coils. This box is actually, if you've ever been in an optics lab similar to this, I hope that you are wowed by how small this is, because usually all of this takes up about 2 tables that size. But we have it reduced to about this size, and this contains all of our optics. It contains the vacuum cell and everything else. At the top of this vacuum cell is something called an atom chip. It's actually part of the vacuum cell, and we can use it for rapid control, rapid and fine control of the magnetic field just below the surface of that chip, which is where your condensate is born. Now, we actually want to do things with the condensates other than just make them, as cool as that is. So on top of all of this is what we call a projection system. This shines light through a window in the atom chip. And with this, so here is a picture of a similar BEC that I showed you earlier. This BEC sits in a potential well. So this is what kind of holds it in place. But we use this light to create features in that potential well. And you can use that to make these barriers. You can also move the barriers around in time and kind of slosh it around. You can do funnier landscapes. Actually, I think this is sign language for quantum entanglement. I forget. But you can do really cool things. We currently have this in 1 dimension. It's actually a method called painted potentials, but we hope to expand that into 2 dimensions here soon. So why do all of this? Well, other than being able to explore just really cool quantum phenomena, you can use this for diverse research applications. We have a couple research groups actually around the world using Oqtant right now when they intend to publish. So when that happens, we will make sure everybody knows because it's super exciting, and education and workforce development. So not just the next generation of quantum experts, which we have already been used in a number of physics labs at universities, physics classrooms. I think the feedback we got was that it was the most fun part of the semester, and they felt like they were doing real science because they knew that what they were doing was interacting with a lab like this. But you can also explore ways to take advantage of these quantum phenomena for, practical applications. We're here to talk about Atomtronics today, so I'm going to now hand it over to Yewei.
Thank you, Alex, for the intro. It's really fun playing with quantums, and here we're going to discuss a little bit about first of all, a brief overview of Atomtronics, and this start with the beginning of the history of the modern information technology, and then we'll explore the evolution from electronics to photonics, and finally to Atomtronics, discussing the development and applications of each. And ultimately, the most fun part, we will conduct a few simple experiments with our Oqtant system. And since we're still online after the webinar, you're free to try with your own jobs to explore it a little bit more. Okay, so Atomtronics is a field that emerged at the beginning of this century, notably pioneered by Dana Z. Anderson, who is also the founder and CTO of Inflection. And this work is also in collaboration and worked with other people, including Mary Holland, other colleagues, and of course, other research groups. And this Atomtronics involves the study and mainly involves the study and manipulation of the ultracold atoms that are arranged in the matter wave circuits that mimic the behavior of electrons in electronic systems. This term, the Atomtronics, actually blends the atoms and electronics, reflecting its focus on creating the atomic analogs of electronic components, such as diodes, transistors, and batteries, etc. These atomic systems, usually controlled by optical lattice or magnetic traps, offer a platform for exploring a quantum phenomena with potential applications in, for example, quantum computing, precision measurement, and novel quantum technologies. So the root of so everything starts from the information processing, and that is what we're trying to do with the Atomtronics. So the actual roots of the modern information processing machines can be traced back through the history of the radio and the signal processing. So the radio development began in the late 19th century with the discovery of the electromagnetic waves, where those waves can carry the information and can carry those information and transfer into other places. Then the introduction of the frequency modulation in the late 1930s significantly improved the sound quality and reduced the interference. This really enhances the signal processing capabilities and make a big advantage on the information processing. Then the invention of the transistor in 1947, which replaced the vacuum tubes, truly revolutionized the field. The transistors were much smaller, more energy efficient, more reliable, much faster, and cheaper than the vacuum tubes. As a result, the transistors became the cornerstones of the modern electronic information processing. So, as previously discussed, it has become essential to modern electronics, serving as the fundamental components in countless devices. For example, today, the integrated circuits in the latest iPhone contains around 10 billion transistors, performing tasks as signal processing, amplification, switching, modulation, and regulation. While the battery forms as the core and the heart of the system by providing the energy for the transistor and the circuit for doing this information processing. Transistor is a semiconductor device used to amplify or switch electronics, as we described earlier. It is made of semiconductor materials like silicon and has mainly three main parts, like emitter, base, and collector in a bipolar junction transistor BJT, or source, gate, and drain in a field effective transistor. This transistor works by using a small input voltage or current applied to the gate to control a larger current between source and drain. This system could be simulated in quantum regime where we build the atom transistor as shown on the right. So atom trapped on the left while with certain temperature or we say chemical potential provides the source. With the optical potential as shown in green, we could generate the tunable source bias as shown as VSS, signal source potential, and gate drain potential, and that could be a simulator of a transistor in atomic regime. This atomic transistor could be used to generate, amplify, and otherwise control or manipulate not electromagnetic waves, but matter waves, which is just as the functionality of the classic electronic transistor. Therefore, it could potentially be as generically useful as the electronic transistor. Benefit from the quantum coherence. Atomtronic transistor provides an entirely different gain mechanism than found in other quantum contexts, including stimulated emission, such as the one you see in lasers, and a parametric gain, and also like four-way mixing gain. Therefore, the quantum atomtronic transistor could enable a true matter wave analog to the lasers. If we take a step back and revisit the concept of the basic electronics by examining a driven oscillator, as depicted on the bottom left, a typical driven oscillator includes a gain medium, a frequency selective component, a feedback loop, a power source, and coupling to the environment, often modeled as a going into the vacuum or into ambient environment. This classical oscillator transmits a quantum coherent electromagnetic wave composed of photons. Well, in 1960s, the invention of the laser introduced the optical analog of a driven oscillator in classical circuits. In a laser, the gain medium is provided by excited atoms in a medium such as a crystal or some gas. Then with the feedback supplied by an optical cavity, the power source such as the current or light pumping the gain medium leads to the generation of a directional quantum coherent electromagnetic wave. Similarly, we can draw an atomic analog as shown on the top right. Here, the gain is provided by an atomtronic transistor powered by the generation of the cold atoms or a Bose-Einstein, or we say Bose-Einstein condensate, which then eventually produce a coherent matter wave. So what are the differences? Here we present a comparison of the specs among electronics, photonics, and atomtronic systems. First of all, these manipulate different particles and waves to process information. Electronics use electrons as the information carriers, characterized by the strong interaction and a relatively slow speed compared to the light, which is about like 10 to the 8th meter per second maximum. Photonics, on the other hand, utilize photons, which moves at the speed of light and are typically non-interacting. Atomtronics involves atoms, which interact modestly and also move at the speed of light in wave-light states. While electronics and photonics are typically coupled with their environment, Atomtronics are more isolated, allowing for highly controllable and sensitive quantum information processing, making Atomtronics a unique platform among the three. Well, despite this difference, all three is aiming to efficiently control the respective carriers for various applications, including information processing and sensing. So why Atomtronics? So besides those, Atomtronics offers several advantages over classical electronics, particularly in applications where quantum effects, lower power consumption, and precisions are critical. By manipulating neutral atoms, often in ultra-cold environment like Bose-Einstein condensate, Atomtronics generate minimum heat and minimum power loss, unlike the classical circuits that suffer from resistive heating. Atomtronic devices maintain quantum coherence and their superfluidity, enabling the new quantum device and architectures that exploit phenomena like interference and entanglement. Additionally, unlike the classical circuit that requires manufacturing in the lab, in the real lab or in a real fab, Atomtronic systems can be easily tuned and reconfigured by your wish in real time, and that provides a great flexibility. This precision, control, and adaptability makes the Atomtronics a promising technology for advancing beyond the limits of classical electronics. I just want to make it really clear that Atomtronic has the potential to complement or enhance the classical electronics in certain areas, but so far it is still in development phase. Therefore, it is unlikely to be completely used to replace the classical electronics. So here I like to show a three simple example of the Atomtronics. So a Bose-Einstein condensate, that Alex just described earlier, can serve as a highly efficient and quantum sensitive battery in Atomtronics. So in this fifth state of matter, atoms are cooled to near absolute zero, causing them to occupy the same quantum state and behave collectively as a single quantum entity. This unique property allows the Bose-Einstein condensate to store and then release the energy with extreme precision with minimum loss, making this BEC an ideal battery for powering the Atomtronic circuits. The coherence and control offered by this battery enabled highly sensitive operation in quantum devices where traditional electronics would fall short. On the bottom right, here we show a battery where we have a lot of rubidium atoms stored in a trap. You can think of a BEC like a battery, while a familiar electrical battery operates at a fixed electric potential, or you call it voltage. An Atomtronic battery operates at a fixed chemical potential for a neutral system. This makes the BEC a promising component for advancing the quantum technologies in Atomtronics. So besides that, you can also create a wire for a current of neutral atoms by forming a flat potential surface that is bounded on the side using a magnetic field and a painted potential landscape as shown on the bottom right. By applying a blue detuned optical light, a repulsive potential is generated, which lifts and separates the atoms as shown on the bottom center. As seen on the bottom right, we can create multiple repulsive forces, and that could form an arbitrary structure of the battery or the atom source we want. As seen on the top left, a large Atomtronic battery BEC can be created and then divided into two separate batteries by introducing a single optical barrier. And yeah, as I described earlier, you can do as you wish. You can move them around. You can suppress them, and you can do it as you wish. Furthermore, as we mentioned earlier, a completely arbitrary painted landscape can be applied for more complex manipulations, and this enabling a precise control of Atomtronic circuits and devices. In the electrical analogy, for current to flow once the wire is connected to a battery terminal, either A, the wire must close the loop and connect to the other end of the battery, or the wire must connect it to a ground or a external load. With Oqtant, we can effectively ground our wire using the terminator beam, which define the zero chemical potential, or you can say the zero voltage in electronic words. This is a crucial ingredient for studying the circuit elements with Oqtant that allow us to make currents. This is achieved by applying a terminator beam, as I mentioned earlier, on the right-hand side of the well, where we are connecting the atoms to the vacuum. The equivalent electronic circuit is shown on the right, where you can see by applying a terminator beam, we are effectively creating a zero voltage, and we're creating a load, a dissipating atoms into the vacuum. Here is an overall summary of the sample circuits and experimental result we discussed in the previous slides. We demonstrated configurations such as two separated batteries, then connect these two batteries by linking them together, and eventually a battery together with the battery connected with an external load. Well, the experimental realization might seem straightforward, as I mentioned earlier. It actually demands extensive knowledge and effort to build such devices. Even setting up the hardware alone requires a trained PhD and can easily cost like up to millions of dollars. In Oqtant, we offer a publicly available free platform for everyone to explore the quantum matter world. Now I will show you just how easy it is to run this experiment using our Octagon API. I'm going to show an example notebook that is based on our demo notebook, which is available to all public users. With our demo experiment and walkthroughs, you could get a good understanding of our system and its capability. Then you are able to create your experiment in a few minutes. Now let's run through the script and rerun the above test in just a few minutes. So as you can see on the background, we have our MOT or our BEC, or the representative of the BEC flashing. So that is while we are submitting jobs. And this is an example notebook or script of our Python API. It is very straightforward. You just need to log into your system, get in your log in to your system with your credentials. Then it will show you the remaining free jobs you have and what is running currently in the queue. So here, what I'm doing is pretty simple. Remember, we first create a terminator beam, and this is what I did. I create a terminator beam, lasts for 3 milliseconds, connecting the atom to the vacuum. And I also create a barrier, which is last for about 50 milliseconds. And with that barrier, I'm actually building an insulating wall, and I'm separating the two barriers apart. So with those two parameters, with some very basic BEC settings, I'm able to recreate the previous 3 scenarios where I have 2 batteries, then I connect the 2 batteries together and eventually terminating the battery on the right-hand side. So I'm going to run the script, and you shall be able to see while we are submitting the jobs, we are actively tracking the jobs. And what's more good about it is in your web portal, you shall be able to see the actual status of your job and also the result of it. So we offer two different kind of a platform for you to play with. And now you can see we just finished the first job in, let's say, like 20 seconds. And our second job is just running. While we are waiting, we can take a peek at what was running just now. Hey, we just create two separated, isolated atomic batteries. And while we are talking, we just finished the second job. Which is shown in here. Those are all real time, by the way, you can see. And for the second job, we are actually connecting these two batteries together by removing the barriers in between. And the last one is the terminator job. Yay, you can see by applying a terminator beam, we are connecting or draining our atoms not into ground, but into vacuum. All right, our jobs are complete. And to make it more flexible for researchers to study, we offer a very comprehensive tool for user to plot, to analyze the data they got from the experiment. And similarly, we offer some other tools. For example, we are able to show the actual potential energy we just ran. You can see we are showing we are forming a potential in 50 millisecond and is growing up in time. And at the same time, we are shining a terminator beam on the right side of the well. And also, you can actually check the intensity of your terminator beam and the detuning, and you can see that to make sure you get a everything match up what you think, and you are doing the right experiment as you wish. So if this seems to be a little complicated for like a grad student or undergrad who has no background with Python, don't worry about that. We offer a graphic user interface, which is called web app. And now I will hand it over to Alex, who will have a brief introduction for that.
Great. So you already saw a little bit from Yewei kind of showing where you can see some of your job results. If we jump back into the dashboard, this is kind of your landing page in your account. I think I've mentioned it a couple times, but you can register with Oqtant for free. You actually get, well, Yewei and I have superpowers, so we always have 1,000 credits, but everybody gets 100 credits per month for free, and you could submit up to 20 per day, and that's any day, whether or not we're online, and any time. But you can also purchase as many as you need. So it's kind of a tailor your experience to what you need. We also currently show the machine status. So Oqtant runs what we call heartbeat jobs. So making sure that the system is running as expected. So this was the last heartbeat job. These are, we splice them in between users, so they're not interrupting your runs. But you can see that the last one that the system automatically ran was at 149 nanokelvin. We also have kind of our online schedule with some upcoming online periods. You can check out whether we're actively online or offline up here. You can see kind of what amount of time you have to wait for your next job to run once the machine is online. So sort of your queue position. And then here's a preview of your recent jobs. And you can also create new jobs this way. Additionally, we have some resources, including kind of our user guide, another introductory video, a web application tour, so it can kind of walk you through. It'll automatically pop up when you create a new account, but you can launch it from any time here. A link to our Slack channel, some FAQs, and then we also started creating these technical notes, we call them, but they are just short little mini chapters about some of the more important aspects of working with Oqtant. Our Oqtant API, which we just ran through with Yayway. We actually have a whole other page with our kind of, so we're hosted on GitLab, but this is a more user-friendly, so you can actually go through a lot of the Python notebooks without launching anything yet. So it's helpful without digging in, but we definitely recommend that you download Octopi soon so you can play with what some of the similar things that Yayway just showed us. We have installation instructions here, but probably more important, or more interesting at least, we host about, what is that, 13 example notebooks and growing. So starting with a hello world, we also have a series of walkthrough notebooks. So this gets you familiar with the API as well as Oqtant's capabilities and functionalities, including like optical landscapes. But then the Terminator, Atomic Terminator walkthrough, I just linked it in the chat. But this is what Yayway's notebook, he based this off, but tailored it specifically for our webinar today. But you can go in and dig into this as well. And then what we're also really excited to continue growing are our demo notebooks. So you can do really cool experiments, just hit go. And you can do like this is similar to what Yayway has shown a few times, where you can actually make a grading pattern with optical landscapes and look at, I'm going to scroll really fast. This is an interference pattern of quantum matter interfering with itself, similar to how you would see with like a multi-slit experiment using light. You can also look at the speed of sound. You can measure the speed of sound in quantum matter, just like in other medium. So I think we can head back to the PowerPoint and kind of wrap things up. Obviously, if you haven't figured out already, you can ask questions in the chat, and then we'll have some time here now to go through any more questions you have live. So you can sign, this QR code will take you to the Oqtant web application where you can sign up for a free account. It's also pretty easy to remember, I think. It's oqtant.inflection.com. Poke around there, take the tours. You can install Octopi from the document page I just showed you. You check out those notebooks. And like I mentioned, you can submit your jobs anytime. I also wanted to plug our upcoming webinar in about a month. Our colleague Charles Williams will be hosting Cold Atoms in the Classroom, a better way to teach atomic physics. He's the product manager for a lot of our really cool quantum hardware products, including those meant for education and workforce development. So this QR code will take you to a registration form similar to what you already used to get here today. So thank you. Thank you all for joining us. We'd love to hear more from you. If you have any more questions, comments, or feedback, please drop it in the chat, or and we'll go through it now. But also, if something pops up later, please feel free to email us. This is a QR code that will take you to the Oqtant Slack workspace. So you can chat with us in more real time. A lot of our team monitors that pretty regularly. And even cooler is more Oqtant users like yourselves are also online. So you can kind of come up with ideas and answer each other's questions as well, because there's a much bigger world out there and much more ideas than what we can even come up with, even though we're pretty obsessed with this. And we'd also love feedback on what did you think of this webinar? Is there any other anything else you would love to hear from us on Oqtant or from Inflection? Please let us know. And thank you, Yayway.
Thanks.
All right, so let's jump into the chat so you can see it from over here.
Yep.
All right, Isaac asked, does that idea of Atomtronics work on a quantized atom?
Yeah, that's a good question. So that is related to the Atomtronic battery we mentioned earlier, because that battery is basically providing the the sources or the resources for us to do those kind of computation or manipulation. So yes, we are using a really cold, really single state atom, which is called a BEC. So yes, it is quantized.
Thanks, Yewei. And then Sunil asked, what sorts of research work can I do from here? Well, it's pretty broad, but do you want to list a couple of your favorites, Yewei?
Yes. So for that, you can do a lot. So a few interesting field would be like inertial sensing. For example, on our system, one of the thing we can potentially do is do a Atomtronic interferometry, and with that, we can measure the acceleration we have on atoms. With that being said, we can measure the gravity, and it could be also be used as the inertial sensor. And more generally, it could be used as like a quantum computing. You can use the coherence and entangled state of the atoms to store the information and observe the evolution of that. So I would say it could be used as a workbench to study the atom behavior using our atom computer, which is really, really hard for a classical electronics or classical computer to simulate.
Thank you. I also one shout out I wanted to give is we can also there are researchers using Oqtant for physics education research.
Exactly.
And we are collaborating with them and should be able to host some really exciting new modules for the classroom that are designed by educators and actually who are researching the efficacy of how useful and how helpful that is those modules are to students, real students.
Yeah, that really reminds me that at least when I was a student, if I need to recreate a very complicated research, that really like freak me out, and there are so many knobs to tune, and when I'm just tuning these, I can easily get myself lost, and either I can make some damage or make things unsuccessful. But with Oqtant, you know what you're doing, you know you're tuning, for example, the evaporation steps. You're not like worrying too much about hardwares, but instead you can really engage on thinking about what you're doing and what should be the outcome. So I think that on the one hand side, really simplified the experiment, really reduce the cost for that, but also making people or students more engaged on this thinking and learning process instead of like trying to.
Yeah.
Yeah.
Yeah, those fiddly bits and like learning how to like fiber couple are super important, but also not being able, a lot of people bring this up. They're like, well, I don't know what I'm doing. I don't want to break your system. You can't break it. We engineered it so that you can't break it. So like Yewei said, you can focus on what you're doing instead of the how. And then you can learn how to do the how in other avenues, like which you can also learn about at our next webinar. Okay. Joshua, cool stuff. Thank you. You mentioned 2D barriers coming soon. Estimate of how soon? We don't have it currently timed. As this is our main production machine and also a development machine, we have to be very cognizant of when we are doing development work versus making sure that we are online when we say we will be, which is our #1 priority. But that's a big goal because we know that 2D painted potentials will really, really open up the application space and for how Oqtant can be used. Greg asked, is it possible to access remotely like through Colab? That's a great question, Greg. We actually, we've been working on expanding ways to program Oqtant. We recently, I haven't emailed everybody about this yet, and we'd love to chat with you on Slack if you have more questions, but we will have that possible here soon or in similar access.
What sort of the research you can do from here? So you can do the like inertial sensing maybe require a little bit more hardware, but so now what you can study is, for example, the coherence of these quantize atomic ensembles, as Alex showed earlier, the quantum interference. And you can study, for example, the soliton excitation, like the collective mode of the BECs, the quantum tunneling effect, and also you can build your real Atomtronics using our device. For example, you can build a real Atomtronics, which I didn't show in this webinar. So those are the things you can study with the current devices.
Great. Sunil also asked, can I estimate the ground energy of the hydrogen atom from here?
I don't think you can.
It's an
No.
interesting question, though.
Yeah.
Samarth. Samarth asked, I like the analogy to the battery connections. How should one think about setting up problems for Oqtant?
How should one think about setting up problem?
Samarth, I think you're on our Slack. Do you want to ask this in there and then we can think about it some more? I want to make sure I understand
Yeah,
your question.
I think that fully relies on your interest and the kind of application you're trying to do, because the real application for Atomtronic is not just like simulating the classical electronics, but more using that kind of analogy to build the stuff that could be more useful for simulating the atomic ensemble, or to study more like atomic phenomena and behaviors. So yeah, we need a more like interest or research like orientated purpose to design the.
All right. Shweta asked, are there any issues or delays you ran into when combining Octant with other analog devices when connected with Python notebooks? If I'm interpreting the question, I think you are kind of, if you're asking kind of about how, like, we actually go from the Python notebook that you are running all the way to this device, what sort of issues or delays? Well, issues, we don't really have any. That's we've done a significant amount of design and testing, verification and validation to ensure that we don't run into many issues like that. And if you're asking about like an actual time delay, so if you submit a job from the notebook or the web application, if there's no one in the queue ahead of you, it can run as quickly as 20 seconds. To go through the entire software stack and run on the hardware and then return the results.
Yeah. And besides that, I think one little issue is we're currently only operating. So currently our schedule is bi-weekly and we're only online for 3 days a week. And also we are mainly on a US time zone. So if you're located in a different time zone, which is like, I mean, don't get me wrong, but a lot of our researchers is like not US based, but I'm sorry, you either have to like stay up a little bit, or you can submit your jobs before you go to bed, and then you shall be able to see your result the next day when you wake up.
Yeah, and semi-related, we actually do offer a simulator, and the simulator works through the Python API, and that runs locally on your system. It doesn't touch your job credits, and you can use that to also vet some of your ideas and your code without needing to wait for the hardware, or if you're trying to be frugal with your job credits. Yeah. Anonymous asked, I am currently on a graduate student with Bachelor of Science in Physics Education, graduating with 3rd class. Is there any course that I need to do that will enable me to research into Atomtronics for my master's? Is there any university that will admit me for such a class? I'm not sure we can actually answer this. I think we can probably provide some papers if you want to learn more about Atomtronics.
Yeah, I think the first step would be go through our basic walkthrough or demos on our web app, and a lot of them has the reference or has a link to the reference or to the paper, which are very closely related to the one we talked earlier today. And besides that, you can always reach us through our Slack channel, and we can provide more info with a pretty short turnaround time.
Yeah, or email as well. All right. Sebastian asked, can a Bose-Nova be created in this experiment stack?
Yeah, there's a lot of things you can create. You can use your Bose-Einstein condensate to create a firework. You can let it explode over time. For example, there's a very typical thing people will do measuring the atom temperature is to release your atoms and let it free fall under gravity. But at the same time, due to the finite temperature of your atomic ensemble, you will see your atom actually expand, or in your word, explode over time. So if you reverse that, it would be like a perfect boson firework. And as we mentioned earlier, we provide the capability of manipulating our atoms. So previously, we even make a little cartoon playing the BEC ping pong.
Awesome. I like the idea of the fireworks. Sunil asked, what part do I have to focus to enhance the Oqtant? What are the limitations of Oqtant? I think this is probably also a specific question if you're wondering about more like specifications or resolution. If you're wanting to ask like how you enhance your experience with Oqtant, I would check out some of the resources we went through, the technical notes on the web application, and our library of demo notebooks. And then I think also the best way to enhance your experience with Oqtant is just joining the Oqtant community, the Slack workspace that we keep pointing out. We have some active users in there. And I love that I actually have seen people start to answer each other's questions before we even get to it.
Exactly. So for example, currently we have some hardware limitation and also some hardware limitations, but the main focus of that is trying to make user has a reasonable or good experience while providing a large enough like flexibility for the users at the same time. So there's definitely a lot of things we can open up the access and maybe the tunability for the users. That is exactly why we want to hear back from you, and what do we want to know from you.
Definitely. All right, we're at 1 minute left, so I think this is the last question we can get to answer. Anonymous asked, in addition to applying optical barriers in landscapes, can you apply other external fields like magnetic fields?
Yes. So far, the hardware have the capability, but considering the people's research and the in-switch, we are not opening it up to the users. But the answer is yes, we can definitely do that. If you let us know on Slack or by email telling us, hey, we need this capability, we can definitely figure it out and make it available for you.
And I would also bring up the RF evaporation steps. So that's one of the last and more important steps in creating your BEC. You have control over that. And we have more about what that means. Like, what is an RF evaporation? What does that mean? We have a technical note for that as well. Well, I think we are at time. Thank you all so much for joining us today. Please keep sending us all these great questions. If you have more ideas, if you want to do any projects, we'd love to learn about them. If you do something really cool, tell us, and we'd love to promote what you're working on too. Two-way street. Well, thanks so much for joining us, and we hope to see you at our next webinar on September 17th. All right.